So use the adjoint theorem to find the inverse of the matrix. In the adjoint theorem simply said that the A inverse is equal to 1 over there's something up with this computer. 1 over the determinant of A times the adjoint of A. And you recall from yesterday that the adjoint is the transpose of the matrix of cofactors. So here we take the matrix A and we find all of its cofactors. And so here we stated I'm looking for the matrix of cofactors. Take the first position, and we'll find the cofactor, which is the minor times the sign, right? The sign is either negative or positive, depending on the position. If the position is even, then the sign is positive in front. If the position is odd, then the sign is negative in front. So here we take the position where this 2 is, we delete its row and column, and so now this is the matrix of the subdeterminant. So here, this is the determinant of the submatrix, excuse me. So this would be 3 times negative 4 is negative 12 minus 0. This is just negative 12. And that position here is positive, but that number is negative, so it stays the same. We move over here to where the 0 is, delete its row and column. So it's the matrix of the determinant of the submatrix over there. So 0 times negative 4 is 0. Then it's minus negative 4, which is positive 4. But this position here is odd. So here we have 0 plus 4, which is positive 4, but the position is negative times the 4. We move to where the 3 is, delete its row and column. The determinant of the submatrix is 0 minus negative 6, or 0 plus 6 is positive 6. The position here is positive. I think the trouble may be in this pen. Yeah. Move to where the 0 is, delete its row and column. So this becomes the determinant of the submatrix. 0 times negative 4 is 0, minus 0 is 0. And the 3, we're at the 3 in the middle, delete its row and column. So this becomes 2 times negative 4 is negative 8, plus 6, negative 8, plus 6, negative 2. We move to where the 2 is, delete its row and column. This becomes 0 minus 0 is 0. Move down to the last row. At the negative 2, delete its row and column. So this becomes 0 minus 9. So this is negative 9. Here, the position is even. So this is negative times a positive is negative 9. Move to where the 0 is, delete its row and column. So this is 4 minus 0. So this is positive 4, but the position here is odd, so it's negative 4. Then we move to where the 4 is, delete its row and column. This is 6 minus 0 is 6, and the position there is even, so it's positive. So this is the matrix of cofactors. Take its transpose and we get the adjoint. Now, I stated there that the determinant was -6. I didn't solve for that, so let's just solve for that quickly. I'm going to find the determinant of A by cofactor expansion along the second column. You see that? It's a 0 there, it's a 0 here, so all you're doing is saying 3 times the determinant of the submatrix, which is the 2, the 3, the -2, and -4. So this is 3 times -8 plus 6. So it becomes 3 times -2, -6. And forgive me, the pen is, this is a electronic pen, so there's no ink in it, but it's acting like it's losing ink. Anyway, go figure, right? So now the inverse is equal to 1 over the determinant of A times the adjoint of A. The inverse of a matrix exists if what is not equal to 0? The determinant. Very good. So on the test, I asked the question, does the inverse of this matrix exist? I'm asking you to find the inverse. Does it exist? So I'm begging you to use that theorem, and I'll state it here again, which simply says that a matrix is invertible if and only if the determinant of the matrix is not equal to 0. Okay? So you just find the determinant. If it's 0, you say the inverse does not exist. If the determinant is non-zero, then the matrix inverse exists, period. So we call this an existence theorem. An existence theorem doesn't tell you how to actually get a thing. It just tells you whether or not the thing exists or not. I stated it yesterday, but it's always good to restate things. The inverse of a matrix exists if and only if the determinant of the matrix is not 0. So the inverse of a matrix exists if and only if, in other words, if the matrix is invertible, that is, if the inverse exists, then automatically you get for free that the determinant will be non-zero. Or the other way around, which is the easier way, if the determinant is not equal to 0, then you get for free that the inverse of the matrix exists. Excuse me, thought I'd put that on silent. So now we use the Adjoint Theorem, and we find the inverse. We divide each term in the adjoint by the determinant, and the determinant we got was -6. So it's -12 divided by -6. We get 2, get 0. -9 divided by, that is -6, so we get 3/2. -4 divided by -6, 2/3. Negative 2 divided by negative 6, 1/3. 2/3 again there. Negative 1, 0, and negative 1. Okay. Good. Now when Dr. Wayne Snodgrass is the pastor of Progressive Union Baptist Church in Huntsville, and if you're privy to have his cell phone number, when you call it, if he doesn't answer, he'll say, "This is Wayne Snodgrass, now you say something." So now I've said all this, now you say something, and you work number 3. So you want to find check to make sure that the determinant is indeed 4. You know, it might not be. Sometimes I put problems here and I put wrong things up there to throw you off. I don't want you to take my word for it. Yeah. Now that's a triangular matrix, so you know that quickly your determinant is going to be the entries right along the main diagonal. Right. 2 times 1 times 2 is 4. That's what you ought to have for the inverse. Okay. James, is that okay? Good. All righty. Lastly in this section, Cramer's rule. Cramer's rule is a method of solving for the a solution for a system without actually utilizing row echelon form, row reduction form. Cramer's rule uses nothing but determinants to solve for the solution for a system. What he does is, given the system AX equal to B, it's a square system with here n unknowns. It would have to be square in order to use the determinant, because you can only take the determinant of a square matrix. The system is said to have a unique solution. If you got n unknowns and you want to be able to solve for them, so x sub 1 to x sub 2 and so on to x sub n, well, the solution is given by the ratio of determinants. So x sub 1 would be the determinant of the matrix A sub 1, where the subscript denotes the column that is replaced in the coefficient matrix with the B column. So here, where each A sub j is the matrix that's determined by replacing that subscript, right, with the entries of the B matrix. And you do that for n terms because you have n unknowns. And so if we give you a 2 by 2, then you'll have 2 of those type matrices. And they're all divided by the determinant. And so today we'll give an example of a 2 by 2, use Cramer's rule to solve for the solution. You can always check your answer by all means by taking your solution, just plugging it back into each equation to make sure that the equations both are balanced. And then the next thing we'll do is an example of Cramer's rule with a 3 by 3. And so, once I do those two, then I would have exhausted the question types that I would pose for you on the exam. So let's look at these 2 examples here. Now, even though I worked through it here, just to put the model of the solution there, it's just always good to make sure that you see it. So this is for number 4. And I suppose we probably could have just picked another problem out of the book as well, since we have that one worked out for you. Book is limited. That was the first exam. They're all 3x3 systems, not a 2x2. Well, I guess that's fine. I use one of those. Let's look at this example and we can just work through it. So the matrix here, its determinant for A is going to be the entry 7, 3, negative 2, and 1. You get the determinant. A sub 1 is the matrix where I remove this first column and I put in its place 3 and 5. So 3, 5, and then negative 2 and 1. You solve and get your determinant. And then A sub 2, I take the coefficient matrix and I replace the second column, replace this column here with these terms 3 and 5. And so X sub 1 is the determinant A sub 1 divided by the determinant of A. And then X sub 2 is the determinant of A sub 2 divided by the determinant of A. And so you get your solution 1 and 2. Let's do this. Let me work this problem, and then I'll pick a problem, some old problem in the book or on an old exam, and we'll use Cramer's rule to solve it as well. So let's look at this one. This is a 3x3. So the first thing we want to do is find the determinant for A. So this is 4, 11, 1, 5, 1, 5, 0, 2, and 2. Now it doesn't say here what method that they want you to use to find the determinant, so whichever method that you prefer is fine. Excuse me. So here, what I'm going to do is to use cofactor expansion along the third column. I'm going to get rid of one of these 2's and then proceed from there. So what I'm going to do is just say negative times row 3 plus row 2. So this is a 10, negative 4, 0, 1, 5, and 2. So this becomes 2 times here. I'm expanding this way. And so this is the 2 times the determinant of the sub matrix, 4, 5, 10, and negative 4. This is 2 times negative 16, minus 50. So we get negative 66 times 2 is negative 132. What about A sub 1, its determinant? So we look at the matrix above, we remove the first column and we replace it with 2, 3, and 1. So 2, 3, and 1, 5, 1, 5, 0, 2, and 2. Again, I'm going to use cofactor expansion along this third column. I'm going to get rid of one of those 2's. So I'm going to say negative times row 3 plus row 2. You remember that property that said that when you're looking for the determinant, if you add a multiple of one row to another row, that result does not offset, does not change the determinant. Okay, so that's what I'm utilizing here. So now I expand along here for the determinant. So this is that 2 times the determinant of the submatrix 2, 5, 2, and negative 4. So negative 8 minus 10. So here we get negative 18 times 2, negative 36. A sub 2 take the coefficient matrix, replace the second column with 2, 3, and 1. So 4, 11, 1, 2, 3, 1, 0, 2, 2. All right. So again, I'm going to expand along for the cofactor expansion. I'm going to expand along the third column. I'm going to get rid of this 2 here. So we'll say negative times row 3 plus row 2. So this is 2. You can kind of look at it and see what happens. This is 2 times, parentheses, 8 minus 20. So we get negative 24. A sub 3. We take this coefficient matrix, replace the third column with 2, 3, and 1. So 4, 11, and 1, 5, 1, 5, and then 2, 3, 1. Right. Well, let's see. However you want to do this is fine. I'm going to exchange rows 1 and 3 to put the leading one up top, if you will. Let's see. I'm going to get rid of this 5 right there. I'm going to say negative times row 3 plus row 1. So that'll be a 3, a 0, a 1, 11, 1, 3, 1, 5, 1. And then try to make the math a little bit easier. I'm going to use this 1 to get a 0 here, and then after that we just use cofactor expansion and just reduce it. So this is just negative 1 times row 1 plus row 3. I'm going to go ahead and see what else can I do. That's fine. I'm going to expand along the first row. So this is 3 times 1350. The sign in front is positive, positive, negative, positive. So plus the 1. Come here to this 1, expand along that position. Let's use red, different color. So this is 11, 1, negative 2, and 5. Right. So we work that out. This is 3 times, this is 0 minus 15, plus here, this is 55 plus 2. So a sub 3, the determinant for a sub 3 is negative 45 plus 57. Looks like 12. So now, we got the setup there for you, but x sub 1 is the determinant for a sub 1 divided by the determinant for a. Right? The determinant for a sub 1, we found that to be negative 36. The determinant for the matrix itself, we found that guy to be negative 132. So that gives you 3 over 11. X sub 2 is the determinant for a sub 2. Excuse me, we found the one for x sub 1. All over the determinant for a. Well, the determinant for a sub 2 is negative 24. That's divided by negative 132. So it gives you this. So you get 2 over 11. Then x sub 3 is the determinant for a sub 3 all over the determinant for a. And we got the determinant for a sub 3. We just found that guy to be 12 over negative 132. That gives us negative 1 over 11. So you put them all 3 together, and you get the solution for that system. Here, the goal is it possible to find the solution for a system without utilizing row-reduced echelon form, and here by using nothing more than determinants. The first time that this system came about was actually Cramer himself worked for an insurance company, and he was computing, back then, years ago before computers. So they had all these grids of all these financial terms for annuities and that kind of thing. And he noticed certain patterns in terms of trying to reduce, trying to solve, looking for certain points on the grid, and just taking these systems of equations and trying to solve for was becoming very cumbersome. So he noticed the pattern with the determinant. So he was able to figure out the patterns of the various determinants to be able to solve, get the same solution, versus if he was actually using Gauss-Jordan form or what have you. Actually, at that time, it was just the elimination or Gaussian elimination that they were using. And they had very humongous systems that they were solving by hand. So this was an attempt to try to get at that. Now, you may say, well, this is cumbersome too. Well, actually it is. But if you had a grid of all these data points, and if you could kind of see some correlation, a lot of these terms ends up repeating with a very humongous system. A system like, 20 by 20 or something like that. You couldn't even imagine trying to solve something like that by hand, right? Well, if you had something like that having to solve by hand without computer technology, this would be the go-to point to try to reduce those particular systems. Any questions? I failed to ask you, are there any questions from the homework? We got 2.1, 2.2, and 2.3. I'm finished now with 2.3. Any questions from the homework? All right. It seems like if I get off my track and do something different than what have planned to do, it throws off my time. So let me look at the sample exam. I want to give you a problem in class to do for Cramer's rule. Do you think you have this right here? It's pretty straightforward. Is that okay? Okay. So we'll move on, look at the sample exam. That'll give me time to kind of talk about two problems on here that I think always give students some issues. All of the problems on the sample exam are already worked out in Blackboard. You can go and look at that, and they're all worked out in detail for you. But let me just make mention of two of those, and then we'll look at the page that has the monster theorem on there. You want to make sure you know that, and the true and false questions for section 2.3. Okay?